Now you've got binary, and you can use those learning science tools to make it permanent and someday be able to really read binary fluently if you choose. You can become what I consider to be super cool. So you know binary is the language computers actually speak. But if you ever looked at a MAC address, examined a memory dump, analyzed malware, or any other number of examples, you've seen stuff that doesn't look like decimal, and it certainly doesn't look like binary. You've seen combinations of numbers and letters like 4D, 5A, or FF colon, AA colon, BB colon, CC colon, DD colon, EE colon. Sorry, no colon at the end there. Just EE. Well, that's hexadecimal, and it's everywhere in cybersecurity. Hexadecimal exists, like we talked about, because people have a hard time with binary. Binary is perfect for computers, on-off transistors. A single byte, just 8 bits, looks like 11010110 in binary. And if you're like a lot of people, when you just start hearing me say 011, you just glazed over, tuned out. Now that's 8 characters to represent 1 byte. So imagine looking at a memory dump containing thousands of bytes. You're looking at this, it's all strings of ones and zeros. I say beautiful, but no, most people don't. You go cross-eyed within minutes, and you're having trouble spotting patterns and anomalies. So the solution that they've given us to solve this problem is hexadecimal. That same 8 numbers, 11010110, becomes simply D6 in hexadecimal. That's it, 2 characters instead of 8. We like to shorten things, it makes it easier for us. A 32-bit IP address that would take 32 binary digits can be expressed in just 8 hexadecimal characters. So the majority of people prefer hex over binary as their notation to read when working with computer data at a low level. Now, this didn't come out in the age of AI. It's an old thing. The concept of base 16 counting, that's hexadecimal, is old. The mathematician and philosopher Gottfried Wilhelm Leibniz, the same person credited with developing the binary system and co-inventing calculus, experimented with base 16 arithmetic in the late 1600s. He originally called it SE decimal or C decimal, and he worked out conversion methods. He notated and used musical symbols, UTREME, mi, fa, sol, la, ti, do, rather than our modern A through F. I added the T-do part, just if you've ever seen Sound of Music or had to do these. So the first serious proposal to adopt hexadecimal for everyday use came from John William Nystrom, a Swedish-American civil engineer, in 1859. So it was invented in the 1600s, but in 1859, a couple hundred years later, Nystrom proposed what he called the tonal system. It was an ambitious plan to replace decimal with hexadecimal, not just for mathematics, but for everything. His system included a hexadecimal calendar with 16 months, a hexadecimal clock with 16 hours a day, and even new systems of weights, measures, and coinage. It's like people who love cows, and you see they've got cow wallpaper and cow salt and pepper shakers and cow serving dishes and cow towels and cow pot holders. That was him. It was hexadecimal for everything. He published his complete proposal in 1862. He argued passionately that base 16 was mathematically superior, but the world wasn't ready, and his system never gained traction. The hexadecimal notation that we use today, digits 0 through 9, followed by letters A through F, was standardized by IBM in 1963. That's fairly recent. There's, lots of people alive today that were adults in 1963, I think, but definitely people born well before that, I hope. With the introduction of the System 360 mainframe computer. So the System 360 mainframe, those huge computers, they standardized hexadecimal notation. IBM, the big giant. This wasn't the only notation that had been tried. Earlier computers like the Bendix G15 in 1956 used 0 through 9 and U through Z. Some systems in the 1950s used digits 0 through 5 with special markings to represent values 10 through 15. But IBM's choice of A through F became the industry standard and remains so today. The selection of A through F was practical rather than elegant. Computer scientists needed single characters to represent values 10 through 15. Using the first 6 letters of the alphabet was the simplest solution that worked with existing keyboards and character sets. Now, not everybody loved this. Bruce Martin of Brookhaven National Laboratory wrote a letter to the communications of the ACM in 1968, proposing entirely new symbols based on visual representations of bit patterns. He thought that would be better, but his alternative never caught on. Sometimes the practical solution wins over the theoretically pure one. Yeah, and also if you're IBM, you win a lot, right? Hexadecimal became the standard for representing computer data, partly because it maps perfectly to binary in groups of 4 bits. 4 bits can represent values from 0 to 15, exactly 16 possibilities. And hexadecimal is base 16, meaning it has exactly 16 digits. They are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. This means every possible combination of 4 bits corresponds to exactly 1 hexadecimal digit and vice versa. So you can see the mapping on the screen. 4 zeros in binary is 0 in hex. And notice 0001 equals 1, 0010 equals 2. Did you notice the 1 on the right side was just scooted over 1 space? Now 011 equals 3. So it kept that 1 that was scooted over, but then it added a 1 to the end. Now we've got 0100 equals 4. So we've got that first 1 scooted over to the second place. We've got 5, 0101, 6, 0110, 7, 0111. Can you see the pattern emerging? 1000 equals 8. 1001, 9, 1010 equals A, which represents 10. 1011 equals B, which represents 11. 1100 C, representing 12. 1101 D, representing 13. 1110 equals E, representing 14. And 1111 equals F, which represents 15. So when you get to the point where it's all ones, you've got 15. Because a byte is 8 bits, and 8 divides evenly into 2 groups of 4, every byte can be represented by exactly 2 hexadecimal digits. The byte 11010110 splits into 1101 and 0110, 0110. That's D and 6, giving us D6. If you look at that mapping, 1101 equals D, which represents 13. 0110, we saw in our mapping it equaled 6. So it reduces the math required beyond knowing those 16 mappings. And the relationship doesn't exist with decimal. There's no clean way to split binary into groups that map to decimal digits. That's why you'll rarely see raw computer data displayed in decimal. It requires that calculation for every conversion, and the resulting numbers don't reveal patterns in the underlying binary the way that hexadecimal does. Hexadecimal appears constantly in security work. Understanding where and why helps you recognize it and know better what you're looking at. Like I mentioned, MAC addresses. Every network interface has a unique media access control address, MAC, displayed in hexadecimal. A typical MAC address looks like 00:1A:, 2B:, 3C:, 4D:, 5E, or 00-1A 2B 3C 4D 5E. It can be represented both ways, you'll see sometimes. Those 6 pairs of the hex digits represent 6 bytes, 48 bits in total. When you're analyzing network traffic or investigating which devices were connected to a network, you're working with MAC addresses in hex. So hex, some people call it a curse, but if you're thinking in terms of hexadecimal, a lot of people love it. IPv6 addresses is another example, while IPv4 addresses use decimal notation, like 192.168.1.1 with the dots in between. IPv6 uses hexadecimal. An IPv6 address looks like 2001:0DB8 85A3 0000 8A2E 0370:7334. It's a lot to look at, but as networks transition to IPv6, reading decimal becomes increasingly important for network security professionals. And then we have memory addresses. When you're debugging software, analyzing crash dumps, or investigating malware, memory addresses are displayed in hexadecimal. You might see something like 0x X7FFE0000, indicating a specific location in memory. When you see that 0x, that prefix, that's a common convention indicating that what follows is a hexadecimal number. Now we've got file signatures. Remember, we talked about them in terms of magic numbers that identify file types regardless of what the extension at the end was, whether it says .png or .pdf or whatever. These are also displayed in hexadecimal. A Windows executable begins with 4D5A. That spells MZ in ASCII, the initials of Mark Zibikowski, and that was an early Microsoft developer. A PDF file begins with 25504446, and that spells %PDF. When you're examining files in a hex editor during forensic analyses, you're looking at the raw bytes displayed in hexadecimal. And then we have hash values. Cryptographic hashes like MD5, SHA-1, and SHA-256 are displayed in hexadecimal. An MD5 hash is 128 bits, but instead of showing 128 binary digits, it's displayed as 32 hexadecimal characters. A SHA-256 hash becomes 64 hex characters rather than 256 binary digits. When you're comparing file hashes or analyzing indicators of compromise, you're reading hexadecimal, very likely. And then we've got color codes. Web colors are specified in hexadecimals. Yes, you might have a choice between RGB or hex, right? But we're speaking of the hex side of things. The color white is 6 F's in a row. So you've got your hash symbol, your pound symbol, FF, FF, FF. That's white. Black is pound 000000. All bits off, white, all bits on. And red is pound FF 0000. Each pair of hex digits represents the intensity of red, green, and blue. While it might seem unrelated to security, understanding hex color codes helps when you're analyzing web pages for phishing attempts or examining malicious scripts. And it actually helps in very concrete and technical ways. Visual deception in phishing relies on near identical colors. Phishing pages frequently use slightly altered brand colors. Like, for instance, they might use 0A3CA8E, where the original page that they're copying is actually 0A3C8F. To the human eye, they look identical. Now, if you understand hex, you immediately see this is a 1-unit delta in the blue channel. You know it's not a random value, it's a deliberate near match. In that case, you're seeing the attacker copied branding but didn't extract it directly, or they intentionally nudged it to evade hash-based detection of known templates. Maybe you hadn't thought of that before, but it's a signal. It's not just trivia. That's a signal if you're in cybersecurity. Hex can reveal intent when JavaScript is obfuscated. You might see a JavaScript line with a backslash x23, backslash x46, and then again, and then x30, and then x30, and then 30 and 30. So if you recognize 0x23 equals hash symbol or pound sign, 0x46 equals F, and 0x30 equals 0, you immediately know this will decode to pound FF0000. That's red. Without that understanding, you just see noise. But with it, you might see DOM manipulation, CSS injection, and UI deception in credential harvesting pages, in fake error banners, and overlay attacks. Inline CSS is actually a common phishing attack surface. Phishing kits frequently avoid external CSS files, inline styles to evade CSP or simplify deployment. So if we look at this line, input style, background, F5, 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 border 1 pic, solid, pound DADCE0, you can recognize this as a Google style input field, not by accident, but as brand mimicry. So you can identify brand impersonation even when logs are missing, and you can correlate colors to known software as a service providers. And hex colors often help detect invisible or deceptive elements. Attackers will use colors to hide text, to overlay invisible buttons, and to capture keystrokes. You've got color with all Fs, meaning for the font color in your CSS, and then background for the background color with all Fs as well. White on white, you don't see anything. Or CSS that says opacity 0. So it's there, but it's invisible. So all 6 Fs after the hash symbol equals full intensity on all channels. Same foreground, sound, background means intentionally hidden content. You always note that. Why would you put white on white unless you don't want it to be seen? And these are commonly used for invisible form fields, to overlay credential capture, and for click jacking layers. And red, the pound symbol FF0000 is not an arbitrary color in malicious user experience. Red is used intentionally because a full red channel, FF, triggers urgency. People see it, they know it's associated with urgency. 0, green, and blue prevents calming hues. Phishing pages will often use FF0000 or E53935 or D32F2F. There's patterns that the criminals use. If you understand hex, you can recognize how aggressive the color is numerically. You can compare intensity between variants. What psychology is going on here? So it matters when you're comparing phishing kits, writing detection signatures, explaining why a page feels urgent. And hex is the bridge between visuals and bytes. Hex is a human-readable representation of binary, and it's exactly what you see in these memory dumps, network captures, and encoded payloads. Colors are just 3 bytes, RGB. So when you see text FF0000, you're already thinking like a memory analyst or reverse engineer, a network analyst. That skill will transfer directly. Smaller method to help you expand your recognition. Now then there's packet data. When you capture network traffic with tools like Wireshark, the raw packet data is displayed in hexadecimal. Understanding what you're looking at requires being able to read hex fluently. So let's talk about how to do this a bit more. Hexadecimal is a base 16 positional system, which means it works the same way as decimal and binary. Each position represents a power of the base. In decimal, the positions from right to left are the 10 to the 0, tens 10 to the first, hundreds 10 to the second, and so on. In hexadecimal, the positions from right to left are ones 16 to the 0, 16 to the first, 256s 16 to the second, and 4096s 16 to the third. To convert a hexadecimal number to decimal, multiply each digit by its place value and add the results. So let's do a little activity, pause the video, and convert 2F to decimal. The F is in the ones place. F represents 15, so that's 15 times 1, which equals 15. The 2 is in the 16s place. That's 2 times 16, which equals 32. Add them together. 32 plus 15 equals 47. So 2F in hexadecimal equals 47 in decimal. So once you're done with that, we've got this next activity to have you pause and try yourself. Try a larger number, 1A3. The 3 is in the ones place. 3 times 1 equals 3. The A is in the 16s place. 10 times 16 equals 160. The 1 is in the 256s place. 1 times 256 equals 256. Add them up. 256 plus 160 plus 3 equals 419. So 1A3 in hexadecimal equals 419 in decimal. To convert decimal to hexadecimal the opposite way, divide repeatedly by 16 and track the remainders. Next, practice exercise for you to pause on convert 200, the decimal number 200, to a hexadecimal value. 200 divided by 16 equals 12 with the remainder of 8. The remainder 8 becomes our rightmost digit. 12 divided by 16 equals 0 with the remainder of 12. The remainder 12 is C in hex. Reading the remainders from last to first, C8. So 200 in decimal equals C8 in hexadecimal. So C is 12 times 16 equals 192 plus 8 equals 200. You do that to verify and it checks out. Like we talked about, where hexadecimal really shines is in converting between hexadecimal and binary. It's just a memorization of 16 mappings. You just memorize 16 things. To convert hex to binary, replace each hex digit with its 4-bit binary equivalent. So we want to convert A7 to binary. So we know A is 1010. 7 is 0111. Put them together, we have the binary number of 10100111. To convert binary to hex, group the binary digits into sets of 4 from right to left, then convert each group. So we split our groups of 4 1101 and 1110. 1101 equals D. 1110 equals E. Put them together, we have DE. If the binary number doesn't divide evenly into groups of 4, pad it with zeros on the left. For example, 10, 1101 becomes 0010, 1101, which converts to 2Z, 2D. There is no Z in hex. So those 16 mappings between hex digits and 4-bit binary patterns are foundational. You want to know them automatically. Let's think of some patterns that can help with that. The digits 0 through 7 follow the same pattern as 3-bit binary, just with the leading 0. We know 0 is 4 zeros, 1 is 3 zeros finished with a 1. Up through 7 is 0, 1, 1, 1. If you know 3-bit binary, which you practiced with your 4-bit conversions minus the leftmost bit, you already know half the mappings. The digits 8 through F are the same as 0 through 7, but with the leftmost bit flipped to 1. 8 is 1000, like 0, but with the leftmost bit on. So instead of 0000, it's 1000. And 9 is 1001, A is 1010, and so on through F at 1111. Some digits have memorable patterns. 5 is 0101, alternating bits starting with 0. A is 1010, alternating bits starting with 1. F is all ones, all bits on. 0 is all zeros, all bits off. These anchor points help you reconstruct others by the process of elimination at the very least. Powers of 2 stand out. 1 is 0001, 2 to the 0. 2 is 0010, 2 to the first. 4 is 0100, 2 to the second. 8 is 1000, 2 to the third. If you know your binary place values, you already know these 4. Different contexts do use different conventions to indicate hexadecimal. The prefix 0x is common in programming and memory addresses like 0x, 1A, 3F. However, the prefix of a $sign is used in some assembly languages and older systems, so instead of 0x, 1A, 3F, you'd see $sign 1A, 3F. The suffix H is used in some documentation, so you wouldn't have the 0x and you wouldn't have the $sign, you would just be 1A, 3F with the lowercase h at the end. In HTML color codes, hex values are preceded by the pound symbol or the hashtag. MAC addresses use colons or hyphens between byte pairs. In file signature tables and hex editors, bytes are typically shown as space-separated pairs, so they don't have the colon or the dash. Being able to recognize these conventions helps you identify hexadecimal when you encounter it in different tools and documentation. So you now have 3 number systems to work with: decimal, binary, and hexadecimal. The relationships between them form a web of connected knowledge that will serve you throughout your cybersecurity career. We want to talk about how to build fluency efficiently based on what learning science tells us. Focus on those hex binary mappings first. The 16 mappings between hex digits and 4-bit binary patterns are that foundation. Once you know these cold, converting between hex and binary becomes instant. Use the chunking principle we discussed earlier. Group the 16 mappings into 4 sets of 4. So we've got 0 to 3, 4, 7, 8, B, C, through F. Master one set before moving on to the next. Research by George Miller and later by Nelson Cohen established that working memory handles about 4 chunks comfortably. So 4 sets of 4 mappings fits how your brain naturally processes information. And interleave your practice. So don't practice hex to binary conversions 20 times in a row, then decimal to hex 20 times. Don't do that. Research by Doug Rohrer and others demonstrate that interleaved practice, mixing different problem types, produces the better long-term retention, even though it feels harder during practice. Remember, pain is gain. Create a practice routine that mixes hex to binary, binary to hex to decimal to hex, and binary to decimal, and decimal to binary. The context switching forces you to identify which conversion process applies, which builds deeper understanding, then drilling one type repeatedly. And the spacing effect, first documented by Hermann Ebbinghaus in 1885 and confirmed by hundreds of subsequent studies, shows that distributed practice produces dramatically better retention than massed cramming practice. A meta-analysis by Cepeda and colleagues found that spaced practice outperformed massed practice in over 95% of comparisons. Practice hex conversions for 15 minutes today. Practice again in 2 days. So skip a day. Then skip 3 days and practice again in those 4 days, and then wait a week and then practice again. The forgetting that is happening between the sessions is not a problem. It's the mechanism that makes spaced practice work. For those of us who are obsessed with learning, it can feel nerve-wracking because you feel like if I don't do it, I'm going to forget. But that partial forgetting is necessary for that long-term retention. That forgetting between sessions is the mechanism that makes spaced practice work. Each time you successfully retrieve information after a gap, the memory strengthens more than it would with continuous practice. So you don't want to just reread the hex binary mapping chart. That's not your most efficient way. And if you rewatch this video, you want to make sure that you're doing the practice exercises and the quiz questions again, something that is creating recall. Because whether it's rereading or rewatching, it is not tapping into that part of you that is different from recognition. Recognition is not what you're looking for. What you're looking for is the ability to do it, to know it thoroughly. You might want to cover up your hex binary mapping chart and write out all 16 mappings from memory. When you encounter a hex value like B7 in your security work, pause and convert it to binary mentally before you reach for a calculator. That effort of retrieval is what builds your fluency. Embrace the difficulty. Robert and Elizabeth Bjork's research on desirable difficulty showed that conditions that feel harder during learning often produce better long-term results. Converting between number systems will feel slow and effortful at first. Sometimes when people find things hard, their brain tries to shut off and they think, oh, it's just too boring. It's not necessarily true that it's boring. It's that it's just not easy, and we don't feel like we're getting the reward out of the experience that we want. Because that's one of the reasons why things that are boring today are a lot less boring a year from now, or things that were boring 10 years ago are not boring today, because we understand them better. Sometimes we identify boring with hard, annoying with something that we think we can't do, or doesn't make us feel like superior. It doesn't make you feel superior when you have to struggle to figure something out, but it does help you to grow, and it gives you something that you can't get otherwise. So the struggle is not a sign you're failing, it's a sign that learning is happening. They should have that up on bulletin boards across the world, because so many people could use that information. I could have used that information. So many people feel so disappointed in themselves, when in reality, what they're dealing with is exactly what will help them to get where they want to go. So resist the temptation to always use a converter tool. That's simple. Oh, yeah, I'll just look that up on Google. I'll just type it into AI and I won't have to worry about it. Well, that's fine. You won't worry about it and you won't know it later either. You want to look it up, but only after you have given what is the possible or probable answer, or at least tried. When you're not under time pressure, do your conversions manually. The shorter term slowdown produces longer term speed. Eventually, you'll see A7 and you'll know it's 10100111 without even consciously having to calculate it. Just as you now see the word cat and you read it without having to sound out the individual letters. You're not having to go every time. You just know a cat is a cat. It's not so easy when you're first learning. And for those of us who learned to read when we were very young, we forget the struggle that it can take to learn to read. And this is just another form of learning to read. And memory sticks better when it connects to meaningful context. As you learn hex, look for it in your actual security work. Look for it in your devices. Look for it all around you. When you see a MAC address, mentally convert a byte or two to binary. When you examine a file in a hex editor, identify the file signature and note what those hex values mean. When you analyze a hash, appreciate that those 64 characters represent 256 bits of data. These connections create multiple retrieval paths in your brain. It's physically happening in your brain, giving you these paths to that same knowledge from multiple directions to embed hex fluency within your larger framework of security understanding. You're going to be able to understand more, troubleshoot more things than you ever could before as you continue to build these pathways. Hexadecimal fluency is one of those foundational skills that amplifies everything else you do in cybersecurity. When you can glance at a hex dump and recognize patterns, see ASCII text, spot file signatures, identify suspicious sequences, sequences, you're going to feel like a master. You'll be operating at a level that distinguishes experienced analysts from beginners. The investment you make now in truly learning Hex using the evidence-based techniques that have been discussed in this lesson are going to pay dividends throughout your career. Every time you don't have to stop and calculate a conversion, keep your focus on the actual security analyses. That's your goal. Make the foundational skills automatic so your mental energy goes toward the complex analytical work that really matters.